Hey everybody, welcome back to chemistry. And so we're continuing on in chapter 6, which is a chapter about energy. And so we talked a little bit about what energy is. And now what we want to do is talk about energy in the context of chemical reactions. And so one of the things you might imagine is that if you have a chemical reaction, it could be that as the chemical reaction goes from reactants to products, that will release energy into the environment. Now, another possibility is that for a chemical reaction to go from reactants to products, it must absorb energy from the environment. So my goal in this presentation is to help you sort of understand why is it certain chemical reactions release energy into the environment, and why is it other chemical reactions don't do that, but instead when they go from reactants to products, they tend to absorb energy from the environment. So let's start with two basic chemical reactions. And so here we have one which we all know about, and this is the burning or combustion of natural gas. And so this is the reaction that occurs when you're at a stovetop and you turn on the natural gas, and then you use the energy released from that chemical reaction, say, to boil some water. And so here is the actual chemical reaction. And so you have a source of natural gas. Oftentimes, the molecule in natural gas is a molecule called methane. Its formula is CH4. It will react with oxygen in the air, and then when those two molecules react, they will break down and change into new molecules, which are carbon dioxide and water. So probably one of the things you've noticed is that when this chemical reaction is going on your stovetop, what it's doing is releasing energy into the environment. And so to indicate that this reaction, as it goes from reactants to products, is releasing energy, I'm going to write here as a product energy, because energy is being released into the environment. Whenever you have a chemical reaction that releases energy in the environment in the form of heat, it is called an exothermic reaction or an exothermic process. So again, when you have a chemical reaction as it goes from reactants here to products and releasing energy into the environment in the form of heat, it is called an exothermic reaction. Now, another kind of reaction that occurs is the one that occurs when you have photosynthesis in a green plant. So what happens there is that the green plant leaves will absorb carbon dioxide from the atmosphere, they will absorb water from the roots, and then under the right conditions, they will bind the carbon dioxide and water together to form a more complicated molecule called glucose. Its formula is C6H12O6. And the byproduct of the formation of glucose in the leaf is actually oxygen, which goes out into the atmosphere. Now, for this reaction, it just doesn't really go by itself. You need to add energy to the reaction to get it going. You can guess where that energy comes from. That energy comes from the sun, and the sun will shine its light in form of energy onto the carbon dioxide and water in the leaf, and that will cause these two molecules to bind together with some other molecules and form here the glucose and the oxygen. So here we have a chemical reaction whose reactants must absorb energy for it to go. So if the reaction absorbs energy for it to go, then here as a reactant we have to write energy here. When you have a chemical reaction that absorbs energy in the form of heat, this is called an endothermic process. And so photosynthesis here is an endothermic process. So you might wonder, why is it this particular reaction releases energy into the environment while its other reaction actually has to absorb energy from the environment to get going? And the way we try to understand that is by understanding that these reactions are actually fairly complicated. In both of these reactions, you have reactants whose molecules are atoms bound together, and those bonds are breaking, and then they are rearranging to form product molecules. And the way the product molecules are formed is that the atoms stick together again and form bonds. And so through these processes, you either have energy released in an exothermic reaction or energy that needs to be absorbed in an endothermic reaction. So to understand what happens when we really need to go down into the process of when a bond is broken, what happens to the energy, and when a bond is formed, what happens to the energy. And so to understand that, I'm going to first talk about a situation where we have two atoms and they bind together to form a molecule. What happens to the energy there? And then we'll move on to some more complicated examples. So before I get to that, let me erase the board and I'll get back with you. Okay, welcome back. And so I can really quickly increase the slide. So here I have a description of what happens is when you take two atoms and you bind them together to form a bond to create a molecule. And so I have several points there, but what I'm going to do is I'm going to go over these individual points on the board. So if I can reduce the slides. Okay, so what we're going to do is we're going to look at a very simple example of bond formation. And so here what we're going to imagine is, let's say you have one chlorine atom. Looks like that. And so you imagine this chlorine atom is a neutral atom, and you can look up its location in the periodic table, and it'll tell you that this neutral chlorine atom has 17 protons and 17 electrons. And what we're going to do is we're going to add that to another chlorine atom. It's also neutral, 17 protons and 17 electrons. Now, if you were to add these two chlorine atoms together, they would react immediately. And what they would do is they would stick together and form a bond between each other to form a diatomic chlorine molecule. So let me draw that out. And so what you're going to get when these two atoms stick together is a diatomic chlorine molecule, which might look something like this. So one chlorine atom is there, is stuck to another chlorine there. And so what I'm hoping you'll sort of understand is when you bring these two chlorine atoms together to form the molecule, they form a bond between them. Now, there's something very important that you need to understand. Whenever you take free atoms and you stick them together to form a bond so that you get a molecule, what happens is that you will have energy in the form of heat that is released. So this is energy that is released in the process in the form of heat. So this chemical reaction of taking two free atoms and forming a molecule is going to be an exothermic reaction. Now, very importantly, this example I have here can be generalized. Whenever you take two free atoms and you stick them together and they form a bond between each other, it is always an exothermic reaction, and you will always have energy being released. And we'll talk a little bit more detail about why that happens. But before I talk a little bit about that, let me write out this reaction in a couple of different ways. And so here we're imagining pictures of the chlorine atoms sticking together to form the molecule. Well, another way you can think about it is that here we're going to draw the chlorine atoms as Lewis dot symbols. And so chlorine has 7 valence electrons. So I'm drawing it like that. And we're going to add it to another chlorine here. It has another 7 valence electrons. To show it's a different chlorine, what I'm going to do is draw X's. And so what will happen is they will combine, and then they will form a covalent bond like this. And so basically, this Lewis picture is exactly the same as the picture I drew above. And so again, it's the same process, and so you might expect, of course, a certain amount of energy to be released. Okay, what I'm going to do is draw this again, but I'm going to draw the other chlorines X's as dots, and then I'm going to draw the shared pair as a bond. So hold on just a second, let me do that. Okay, this picture I have below here is exactly the same as the middle picture, except now I have a shared pair shown as a line. And now you can sort of see that that shared pair is the actual bond. And so now it becomes maybe a little bit easier to see that when you take two free atoms and you bond them together to form a diatomic molecule, you'll get the molecule, which is diatomic chlorine, and you'll get energy released. Okay, well, we can write this a couple more ways. And so one way we can write this is we can write it in terms of, say, a chemical equation using symbols for the elements. And so we have one chlorine atom, which is symbolized by a Cl, right? And it reacts with another chlorine atom, which is symbolized by a Cl. And then here, to represent diatomic chlorine, or two chlorine atoms stuck together, we write Cl2. So I'm literally hoping you understand that when you see these two chlorine atoms stuck together in these different representations, that's really Cl2. Now there's one more way we can write this. This chlorine atom really isn't any different than this chlorine atom. I'm just kind of writing them out separately so that you can see that they can bind together to form a single diatomic chlorine molecule. Since these two chlorine atoms are exactly the same, really what we could write is we could write two chlorine like that. And then the product will be diatomic chlorine. So this is, believe it or not, what I've written here exactly the same as everything I've written above. Now, I think it's a little bit easier to understand the reaction with two separate symbols for chlorine. So I'm going to erase this one here. And now what I'm going to do is, from this reaction, I want to talk about the amount of energy that is associated with this bond formation. So here we go. So imagine here, we don't have so much now, maybe one atom of chlorine reacting with another atom of chlorine to form one molecule of diatomic chlorine. Maybe we expand the situation a little bit. So instead of, say, having one atom of chlorine, we have a lot of them. So we have 6.022 times 10 to the 23 atoms of chlorine. So that's a lot of atoms of chlorine, right? And then we have another set of 6.022 times 10 to 23 atoms of chlorine. So I'm hoping what you can imagine is if you have one set of atoms of a certain number and another set of the same atom of the same number, when they bind together, you're left with just one set of that number, right? So you should have 6.022 times 10 to the 23 molecules of diatomic chlorine. And so I think you know at this point that when you have 6.022 times 10 to the 23, that is 1 mole. So here we have 1 mole of chlorine and reacting it with another 1 mole of chlorine atoms, and they produce 1 mole of diatomic chlorine molecules. So why am I saying all this? And the reason is because we have done this experiment in the lab, and we have discovered the amount of energy that is released when you bring 1 mole of chlorine and another mole of chlorine together to form a mole of diatomic chlorine. And that energy happens to be 58 kilocalories. And so here, let me write that here. So when you bring 1 mole of chlorine and another mole of chlorine to form the molecule, 1 mole of that, you're going to get 58 kilocalories of energy released. Okay, so now I need to introduce some terms. So one term I need to introduce is the letter Q. What the letter Q is, it's a representation of the amount of heat released or absorbed in a reaction. So here we can see that in this reaction of bringing two chlorine atoms together to form the molecule, 58 kilocalories are released. So we can imagine the value of Q is 58 kilocalories for this reaction. And so let me write this in another way. I'm going to write it chlorine, and I'm hoping you just remember this is 1 mole, plus another chlorine gives you Cl2. Now, I want to indicate the value of heat released, and so the way I might do that is on the same line, I write the letter Q like this, and it's 58 kilocalories, because that is the amount of heat released. But there is a sign convention. Whenever you have a chemical reaction that is releasing energy into the environment, it's an exothermic reaction, the value of Q is always assigned to be negative. And so you might be wondering, well, that is the case. Why is that the value to be negative, and I'm going to talk about that in just a moment. So to explain that, I'm going to have to erase this and make a drawing. So I'll be right back with you. Okay, so we're continuing to talk about this reaction where we're taking two free atoms of chlorine and we're bonding them together to form diatomic chlorine. This releases 58 kilocalories of energy per mole of single chlorine atoms you bring together here. So we want to talk a little bit about why is this sign of Q negative. And so maybe the best way to understand that is by drawing something called an energy diagram. That usually helps out understanding sign conventions. And so what I'm going to do is draw an X and Y axis here. So here is my Y axis and here is my X axis. So on the Y-axis, we are going to plot potential energy of molecules. And so I'm just going to make my life easier. I'm going to write PE. And I'm really hoping you'll remember PE means potential energy. Remember we talked about potential energy a few play positives before? So molecules can have potential energy. Different molecules have different levels of potential energy. And we're going to map the potential energy of the reactants and products on this energy diagram. So this is potential energy of atoms or molecules. And then on the x-axis, we are going to have the left portion be the reactants and the right portion be the products. And so let's go ahead and map out where the relative potential energies of the reactant chlorine atoms are compared to the potential energy of the diatomic chlorine molecule. Well, one of the things that is helpful to understand in chemistry is that free atoms have relatively high amounts of potential energy, but when you bind them together, their potential energy actually drops quite a bit. And this is one of the reasons why there are so few free atoms in the environment. Most atoms are found bound together in forms of compounds. So for example, you never see a single oxygen atom in the atmosphere. It's always two oxygen atoms bound together. And one of the reasons is free oxygen atoms have a lot of energy and they can lower their energy, which is what they want to do when they bind together. Same thing with elements in the earth. Elements in the earth tend to, for example, like to bind to oxygen in the atmosphere to form compounds which have lower energy. That's a bit of a digression, but the point I'm trying to make here is that these two atoms of chlorine have relatively high free energy. So let's map that. So here I'm going to draw a line here to indicate the relative energy of these chlorine atoms. And so let me mark this. This is energy of the reactants. So I'm going to write reactants here. There we go. Energy of the reactants. Okay. Now here we're going to now talk about diatomic chlorine. Diatomic chlorine is the product, and this energy is going to be much lower. So here now I'm going to map the energy of the products here. So this is the energy of the products. So now I've been kind of speaking in general terms about reactants and products. However, one thing you need to know is that when you're talking about the potential energy of an atom or a molecule, that value of potential energy has a word associated with it. The word is enthalpy. It's spelled E-N-T-H-A-L-P-Y. So when we're talking about the potential energies of atoms or molecules, we are really talking about the enthalpy of the atoms or molecules. And so here, remember, potential energy here is exactly the same as enthalpy of the atoms or molecules. So when we're talking about the potential energy of these reactants, really what we're talking about is the enthalpy of the reactants. Now, the letter symbol for enthalpy is capital H. And so here when you see capital H, I'm hoping you say, oh, this is the enthalpy of something. And so here are the enthalpy of the reactants. And so here we could say this is the relative enthalpy or potential energy of the reactants. So here the reactants are these two chlorine atoms, right? Now let's look at the potential energy of the diatomic chlorine, it's going to be much less, right? So this is the enthalpy of the diatomic chlorine. It's much lower. So you can see for one thing is that the enthalpy of diatomic chlorine is a lot lower than the individual atoms. And so if we wanted to, we could write something like this. We could say the enthalpy of the individual atoms of the chlorine is much greater than the enthalpy of the diatomic chlorine. Okay, so now let's think about what happens as we take these reactants, which is the individual chlorine atoms, and we take them to products. You will notice that the energy or enthalpy of the reactants is much higher than the energy or the enthalpy of the products. That tells you something. It tells you that if you take these reactants and bind them together, you're going to have to get rid of a lot of excess energy so that then when they bind together, they will have the low energy appropriate for a product. So here what we're doing is we are going from reactants to products, and we have to lose a lot of energy into the environment. And so when we go from reactants to products, we lose a lot of energy. This is the heat that is released in the environment, and so this is going to be Q. And so for this process, when you go from atoms to a molecule here, this is going to be an exothermic process because we're releasing energy into the environment. But there's another way you can think about it. You can think about it in terms of the heat that had to be lost into the environment. Another way you can look at it is by evaluating the change of enthalpy from reactants to products. And so I'm going to write here, another way you can think about going reactants to products is to evaluate the change of enthalpy. So this is delta H. So again, this isn't H. We're looking at the difference, the change of enthalpy from reactants to products. Now, very importantly, you need to know how the change of enthalpy is calculated. So the change of enthalpy of any reaction, doesn't matter which one it is going to be equal to the enthalpy of the products minus the enthalpy of the reactants. Now, let's think about what's going to happen in terms of numbers and signs. So in this particular reaction, because the enthalpy of the product, diatomic chlorine, is so low, this is a small number. I'm going to represent this by a little x. However, the enthalpy of the reactants is a much larger number, large x. And so what you can see is because the change of enthalpy is products minus reactants, you can see in this particular reaction that the change of enthalpy of the reaction for this exothermic process is negative. So the Q is the same thing as the delta H. And so if so, they are both negative whenever you have an exothermic reaction. Okay, so now what I want to do is I want to talk a little bit about the opposite reaction. So I'm going to erase this. I'm going to write a lot of stuff here and I'll quickly go through it. So I'll be with you in just a second. Okay, welcome back. And so now what I want to do is compare what we just talked about, where we took free atoms and we stuck them together to form a molecule, and we found that when we formed a bond, energy released. We're now going to talk about the opposite process, where we take a molecule with a bond that's there. We're going to break the bond to form free atoms, but we'll find here energy is going to have to be absorbed. So if I can increase the slide. So here, in this case, I'm now talking about is bond breaking. And so my goal is to go over all those major points on that slide. So if I can decrease the slide. Okay, so what I have on the left side is a situation where we have bond formation, which is what I just talked about. And so here we're taking free atoms with relatively high potential energy, high enthalpy, and we're sticking them together to form a molecule with a bond which has lower potential energy, lower enthalpy. And so what that molecule must do, it must release the energy in the environment to get rid of it. And so because this process occurs and releases energy, this is an exothermic reaction. Now what I'm doing is, you see this equation, which I've been talking about, taking free atoms and forming the molecule from it? I am now going to do exactly the reverse. So here what we're doing is we're talking about a molecule, which is diatomic chlorine, which has a bond. We're going to be breaking that bond, and we're going to break it up into free atoms. And here, this is an endothermic process, and I want to talk about why that's the case. So in terms of the enthalpies of the atoms and the molecule, that hasn't changed from where we're at before. But now here we're starting with the molecule, which has low potential energy and low enthalpy, and we now have to go to products, which are the free atoms, which have high potential energy and high enthalpy. So you have to add energy to this molecule in order for it to get the energy it needs to separate these atoms into free atoms. And so the way we tend to think about this is if you have a molecule, the bond must absorb energy to break up the molecule and give you the relatively high energy free atoms. And so you can actually do a calculation for the change of enthalpy. It is still going to be the enthalpy of the products, which are now the free atoms, minus the enthalpy of the reactant, which is the molecule. But this time, because the atoms, the products, have so much energy, this is a larger number than the reactant, the diatomic molecule. So now the enthalpy change for breaking the bond to get individual atoms is going to be positive in sign. And so Q, the heat, will also be positive. So whenever you have an endothermic reaction, where the reaction must absorb energy to get to a product, there heat is absorbed and Q is positive. So going back to this endothermic reaction, again, what you can see, energy absorbed by the molecule to break up into these individual atoms. Now, this energy that is absorbed by the molecule has a name. It's called the bond dissociation energy, which is BDE is often what's called. And what the bond dissociation energy is merely the energy needed to be added to this bond in the molecule to take this molecule and break it up into atoms. Now, one of the things that you need to understand is that different molecules with different elements bound and on either side of the bond will need different amounts of energies to break them up into free atoms. And so what I want to do is I want to increase the slide. So here, this slide just kind of points out that bond dissociation energies for molecules are different depending on the atoms that are found in the molecule. So the one we were just talking about is this one, the bond dissociation energy for diatomic chlorine. So here, what I want you to imagine is when you see this energy here, this is the energy needed to break the bond and release these individual atoms of chlorine. And it'll take 58 kilocalories of energy per 1 mole of the diatomic chlorine molecule. Now, one of the things I think you can see is that the energy is different for different molecules. So for example, the next one up, here is diatomic fluorine. It doesn't take as much energy to break this bond to release the individual fluorine atoms. It only takes 38 kilocalories per mole of diatomic fluorine. But if you look at the one above that, here it takes a lot of energy to take diatomic hydrogen and separate it into hydrogen atoms. And so in order to do that, you need 140 kilocalories per mole of diatomic hydrogen to break it up into hydrogen atoms. Now, importantly, when we chemists talk about how strong a bond is, that is a reference to how much energy you need to break the bond. So you can see here of the three, it looks like we need the least energy here to break up diatomic fluorine into individual atoms. And so we might say the bond between the two fluorine atoms here is relatively weak. On the other hand, we can see that here we needed a lot of energy to break up diatomic hydrogen into individual hydrogen atoms. And so here we might say that this bond here that requires so much energy to take the molecule and to separate into hydrogen atoms, this is a much stronger bond. Okay, so now at this point, what I want to do is I want to look at more complicated chemical reactions. And then what we're going to try to do is, looking at whether the chemical reaction is exothermic or endothermic, we're going to try to evaluate whether more energy was required to break the bonds compared to the energy that was released when bonds were formed. So if I can reduce the slide. So let's take a look at this chemical reaction here. So this is, again, the combustion of methane. So it's CH4 plus oxygen gives you carbon dioxide and water. And it looks like I balanced the equation, so I'll put a 2 in front of the water and a 2 in front of the oxygen. So to give you an idea of how complicated this chemical reaction is, what I want to do is I want to write out Lewis structures for all these molecules, and so we get a sense of all the different kinds of bonds that need to be broken and formed. So I'm going to go ahead and write out the Lewis structures, and I'll get back with you. Okay, so what I've done is I've written out the Lewis structures for all the reactant molecules here, and then also the product molecules. And so here, methane is a reactant molecule, and I think what you can see is that methane is composed of 4 carbon-hydrogen single bonds. But also, as a reactant, you have 2 molecules of diatomic oxygen. Each molecule has a single double bond. So here, when we're dealing with these 2 oxygen molecules here, we really have 2 double bonds to contend with. So now let's look at the product side. And so we have 1 molecule of carbon dioxide. Here we have 2 double bonds again, but notice the nature of the double bonds are different. Here we had double bonds between oxygen atoms on the reactant side, but here we have double bonds between carbon and oxygen on the product side. And then here we have single bonds for water, and so each water molecule has 2 single hydrogen-oxygen bonds, but there are 2 water molecules here for a total of 4 single hydrogen-oxygen bonds. Okay, now one thing that is helpful to understand how chemical reactions work, a good simplification to understand the process is to think of it this way. When you have reactants, you must break all the bonds here in the reactants. And you might recall, when you're breaking bonds, you are requiring energy. So you need some level of energy to break all these bonds in the reactants. So you're going to need energy to break the 4 carbon and hydrogen single bonds, and you're going to need more energy to break each of these double bonds between the oxygen molecules here. You're breaking up all the bonds in the reactants, you're releasing all these free atoms. The free atoms recombine themselves, and then once they do that, they form new bonds. And so these bonds are new because here, the new bond here are 2 double bonds between carbon and oxygen, which you didn't see before. And we also have new single bonds between hydrogen and oxygen that you didn't see before. But when these atoms form these bonds, the thing you have to remember is whenever you form bonds, you release energy, okay? So now what we can do is we can take some information about this reaction and understand, do we have a case here where we need more energy to break these bonds in the reactants than the energy that is released when we create the products, or is it the other way around? So let's figure that out. So the information that can help us understand that issue is to understand that here we have this reaction here, combustion of natural gas, and here we are given the amount of heat released, the value of Q, which is also equal to the change of enthalpy of the reaction, is equal to negative 213 kilocalories per 1 mole of methane, which is CH4 reacting. Okay, so we know that when this reaction goes, that because the value of heat and the change of the enthalpy is negative, that this is an exothermic reaction. What that tells you is this. After you have broken up all these bonds and you have formed these bonds, you have extra energy left over that is released. So the fact that this is an exothermic reaction tells you something kind of interesting. It tells you that we don't need as much energy to break all the bonds here as the amount of energy that is released when all these products form. So in an exothermic reaction, it is always the case that you will have more energy released when you make the bonds to make the products than the energy that you need to break the bonds in the reactants. That is always true for an exothermic reaction. Okay, we will consider one more reaction. I'll be right back. Okay, so I've written the photosynthesis reaction. So what I'm going to do right now is just go ahead and balance the equation. And so as I recall, you need a 6 in front of carbon dioxide, a 6 in front of water. You can have a 1 in front of glucose and a 6 in front of oxygen. So this is a balanced equation. Now, what you can do is you can measure the heat absorbed or the change of enthalpy of this reaction. And so when you do that, what you find is this. The heat absorbed or the change of enthalpy of the reaction is equal to plus 670 kilocalories per mole, 1 mole of glucose formed. Okay, so what I want sort of pay attention to is the fact that here the value of heat has a positive sign and the change of enthalpy has the same sign. It is positive, and so that tells you immediately that this is an endothermic reaction, which means that in order to take carbon dioxide and water and convert this into glucose and oxygen, somehow in some fashion the carbon dioxide and water must absorb energy to bring them to the level where they can break bonds and reform to form the products, which are glucose and oxygen. So we can sort of ask that question now. Here we have an example endothermic reaction. Is it the case here that the amount of energy that is needed to break the bonds in the carbon dioxide and water is less than the amount of energy that is released when you form the bonds of the products, which are the glucose and the oxygen? Or is it the opposite? And what I'm hoping you can figure out, it's the opposite. If this is an endothermic reaction, it must be that you really needed quite a bit of energy to break up the bonds within the carbon dioxide and water reactants. But when you formed these products and you formed the bonds, not as much energy was released as the energy that was required to be absorbed by these molecules. And so net, basically, you need a lot more energy absorbed to break up the bonds than the energy that is released when you form the bonds, and therefore, that is an endothermic process. Okay, thank you for listening. We'll see you next time.